Module 4, Ethernet for Industrial People, Frames, Media, Limits, and the Truth Behind the Hype. By the time you reach Ethernet in your engineering journey, it already feels inevitable. Everywhere you look, PLCs have Ethernet ports, HMIs speak Ethernet, drives, analyzers, historians, all Ethernet. So it's easy to assume, open quote, Ethernet must be the best industrial network, close quote. That assumption is half right and half dangerous. This module is about understanding why Ethernet won, and more importantly, what it still cannot promise, no matter how fast it gets. Why Ethernet won. Not because it's perfect, but because it's everywhere. Let's start with the uncomfortable truth. Ethernet didn't win because it was designed for industry. It won because it was cheap, open, and massively scalable. The tutorial lays this out clearly. Ethernet hardware is produced in enormous volumes, making network interface cards and infrastructure extremely low cost compared to proprietary industrial networks. The outcome was inevitable. Economics beat elegance. Ethernet offered open standards, IEEE 80203 vendor independence, huge ecosystem support, rapid evolution of speed, 10 Mbps, Inco 100 Mbps, gigabit, and beyond. For engineers and plant owners, this meant easier integration, easier sourcing, easier expansion, and that momentum never slowed. Ethernet's original sin, contention-based access. Now let's talk about the part most marketing brochures skip. Classic Ethernet is built on CSMA-CD, the same contention-based access method we discussed earlier. As the tutorial explains, Ethernet listens, transmits if the line is free, detects collisions, and retries when conflicts occur. This makes Ethern load flexible, simple to implement, but it also makes it probabilistic, and probabilistic systems cannot make timing guarantees. Why this matters for alarms and control messages. Here's the core industrial issue. In classic Ethernet, all frames are fundamentally equal. Access is based on chance, not priority. There is no inherent guarantee that an alarm frame goes first. The tutorial is explicit about this limitation. Open quote, because of its probabilistic access mechanism, there is no guarantee of message transfer and messages such as alarms cannot be prioritized. Close quote, this is not a configuration problem. Sophie Tat. Ethernet assumes, open quote, if something collides or delays, it will eventually get through. Close quote, that assumption is fine for files. It is risky for trips, interlocks, and safety critical signals. Why Ethernet still feels fast in practice. Now here's where engineers get confused. Despite being probabilistic, Ethernet often feels deterministic. Why? Because modern links are fast. Collisions are rare in lightly loaded networks. Switched Ethernet reduces shared medium contention. So most of the time, messages arrive quickly, but most of the time is not an engineering guarantee. In control systems, we don't design for. Average case, we design for. Worst case, Ethernet excels at throughput. It struggles with bounded latency unless additional mechanisms are layered on top. Frames, Ethernet's true unit of communication. Ethernet does not move characters or symbols, it moves frames. The tutorial details the Ethernet MAC frame structure, preamble, addressing, data, padding, and error checking. This framing is powerful. Error detection is hardware-based and tamed. Data integrity is strong. But again, frames are queued and transmitted based on access rules, not urgency. A frame carrying temperature equals 72 degrees Celsius and a frame carrying emergency shutdown now are electrically equal in classic Ethernet. The wire does not care. Media flexibility. Another reason Ethernet's adaptability is one of its quiet superpowers. The tutorial shows how Ethernet evolved to support coaxial cable, twisted pair, fiber optic media. This allowed Ethernet to enter noisy environments using fiber, scale distances uses. Again, not because it was industrially pure, but because it was practically flexible. The industrial reality check. Here's the balanced truth I want you to carry forward. Ethernet won because it's cheap, it's ubiquitous, it's flexible, it keeps getting faster. Ethernet still cannot inherently guarantee deterministic delivery, priority for critical alarms, bounded worst-case latency. Those guarantees must be engineered on top of it, not assumed. And this is the most important mindset shift for industrial engineers. Open quote, Ethernet is a powerful transport, not a control philosophy. Close quote. Once you see Ethernet that way, you stop expecting it to behave like field bus, and you start designing the layers above it more intelligently. And that naturally leads us to the next question. If Ethernet itself can't guarantee priority, how does industry bend it into something trustworthy anyway? That's where industrial Ethernet variants and scheduling intelligence enter the picture. SHARC, Ethernet physical options, cables, segments, and the topology reality check. Up to now, Ethernet might feel abstract, frames flying around, contention rules, probabilistic access. Now let's drag Ethernet back down to the plant floor, where it belongs. Because Ethernet doesn't exist as an idea. It exists as copper, fiber, connectors, distances, and failure points. And once you understand the physical options Ethernet evolved through, one thing becomes very obvious. 10BASE-T didn't win by accident. Ethernet was never one cable, it was a family. One of Ethernet's biggest strengths, and one reason it spread so aggressively, is that it was never tied to a single physical medium. The IEEE 802x3 standard defined multiple physical implementations for the same logical Ethernet behavior MAC logic, different copper and fiber realities. That flexibility allowed Ethernet to survive changing environments instead of being replaced by them. 10BASE-2, thin coax, thin tolerance. 10BASE-2 used thin coaxial cable in a bus topology. One cable, multiple taps, terminators at both ends. Electrically, it worked. Operationally, it was fragile. The segment length was limited, about 185 meters, and every node shared the same backbone. Now think about FA connector. One crushed cable section, one missing terminator, and suddenly the entire segment behaves unpredictably. 10BASE-2 taught engineers an early lesson. Shared physical media amplifies small mistakes. That lesson still applies today. 10BASE-5, thick coax, heavy headaches. 10BASE-5 used thick coaxial cable, longer distances up to 500 meters per segment, higher robustness, but at a cost. Physically, stiff cable, vampire taps, difficult installation. Logically, still a bus, still shared fate, still termination sensitive, 10BASE-5 was powerful but not friendly. Ethernet was new and alternatives were worse. It did not scale well into modern plants. The pattern you should notice. Both 10BASE-2 and 10BASE-5 share the same weakness. Bus topology ties communication health to cable integrity. The cable stops being infrastructure. It becomes a single point of failure. Industry tolerated this early on, but it never loved it. Start 10BASE-T, why star wiring changed everything. Now comes the quiet revolution. 10BASE-T replaced the bus with a star topology using twisted pair cable. Each node gets its own cable, its own port, its own physical path to the hub or switch. The maximum length per node is about 100 meters, which coat B building and plant layouts. This design change did something profound. It localized failure. If a cable fails, one device drops, the rest of the network stays alive. If a connector is bad, troubleshooting is immediate, fault isolation is trivial. This is why 10BASE-T exploded in popularity, not because it was faster, but because it was operationally sane. Star topology, the hidden reliability upgrade. From a pure topology standpoint, 10BASE-T moved Ethernet from shared destiny to isolated risk. Yes, the hub or switch becomes critical. But that's a trade engineers are happy to make because central equipment can be hardened, redundancy can be added, monitoring becomes easy. Plants prefer visible failure over silent, distributed ambiguity. Star topology delivers exactly that. 10BASE-F, when noise stops being negotiable. Then there's fiber. 10BASE-F variants extend Ethernet using optical fiber, giving electrical isolation, immunity to EMI, long-distance capability. Fiber doesn't care about ground loops, lightning-induced noise, motor harmony P-peers. Wherever distances grow, noise becomes aggressive, safety isolation matters. But notice something important. Even fiber-based Ethernet usually keeps the star topology. The medium changed. The topology philosophy stayed. The topology reality. Most engineers miss. Here's the mental model I want you to walk away with. Ethernet didn't succeed because of one cable type. It succeeded because it evolved toward failure isolation. Bus Ethernet failed together. Star Ethernet fails locally. And in industrial systems, localized failure is survivable. The physical layer truth. If you strip away standards and names, Ethernet's physical evolution tells a simple story. Early Ethernet optimized wiring simplicity. Modern Ethernet optimizes operational reliability. That's why 10BASE-T star wiring dominates plants. switches sit in panels like guardians, fiber bridges noisy zones. And once you see Ethernet this way, not as IT tech, but as structured physical risk management, you stop fearing it and start using it correctly. Now that you understand how Ethernet survives physically, the next question becomes sharper. If the wire is reliable, how do we make the traffic reliable? That's where industrial Ethernet variants begin to matter. Ethernet frame structure. What's inside the packet envelope? Now let's open the envelope. Up to this point, we've talked about Ethernet like a highway, access rules, topology, physical media. But when you troubleshoot Ethernet for real, at 2 a.m. with a switch blinking at you, the only thing that actually exists is the frame. Ethernet does not send messages, it sends frames. Everything you care about, timing, addressing, integrity, lives inside that frame. Think of a frame like a registered letter. A frame is not just data, it's data wrapped in discipline. Ethernet assumes the wire is noisy, devices are dumb at the physical layer, meaning must be reconstructed reliably every single time. So the frame is designed to answer 5 critical questions in order. 1, are you synchronized with me? 2, is this frame really starting now? 3, who is this from and who is it for? 4, how much data should you expect? 5, did the data survive the journey? Every field exists for one of those reasons. Preamble. Lock onto my rhythm. The preamble is the first thing on the wire. It's a repeating bit pattern, 10 1, 10 on 10, sent for multiple bytes, whose only job is timing synchronization. Our discussion on synchronous communication, this is it in action. The receiver doesn't care about content yet. It just uses the preamble to align its clock with the sender. No lock, no data. Simple as that. Start frame delimiter, SFD. Now the frame actually begins. Immediately after the preamble comes the start frame delimiter. 1 byte, 1 unmistakable pattern. This tells the receiver, open quote, stop synchronizing, start interpreting. Close quote. Without SFD, the receiver wouldn't know where noise ends and structure begins. This is the trans-EL discipline to data discipline. Destination and source MAC, identity at layer 2. Now Ethernet gets serious. The destination MAC address answers, open quote, who should pay attention? Close quote. The source MAC address answers, open quote, who sent this? Close quote. These are physical addresses burned into network interfaces, not IPs, not host names, not logical constructs. This is why Ethernet can deliver frames RS are confused. Layer 2 identity is brutally literal. If the destination MAC doesn't match, the frame is ignored. No processing occurs. No apology is sent. That simplicity is intentional. It keeps Ethernet fast and dumb. Exactly what a transport layer should be. Length field. Here's how much to expect. Ethernet frames don't have an explicit end of frame marker, so the receiver must know how many bytes to read. That's the job of the length field. This allows variable length payloads, efficient use of B-eng boundaries. If the length is wrong, everything downstream becomes garbage, which is why integrity checks matter so much. Data plus pad, payload, with constraints. The data field carries whatever higher layers want. IP packets, industrial protocol payloads, configuration data, diagnostics, but Ethernet enforces a minimum frame size. If the payload is too small, a pad is added. This isn't inefficiency, it's physics. Ethernet's collision detection logic re-length, so collisions can be reliably detected on the wire. Even when collisions are rare today, the rule remains because the protocol's foundation depends on it. FCS CRC, trust but verify. At the end of the frame sits the frame check sequence, typically a 32-bit CRC. This is Ethernet's lie detector. The sender calculates it in hardware, the receiver recalculates it. If the values don't match, the frame is discarded silently. No retransmission request at this layer. No negotiation. Ethernet assumes, open quote, if integrity fails, H with it, close quote. That separation of responsibility is deliberate and powerful. Why this matters to you as an industrial engineer. When Ethernet fails, it rarely announces why. Frames just stop being accepted. Understanding the frame structure lets you answer questions like, is the problem synchronization, addressing, length mismatch, noise-induced corruption? This is why tools like Wireshark are so powerful. When you capture a frame and dissect it field by field, you're not guessing anymore. You're reading the truth as Ethernet sees it. And that makes this topic perfect for a podcast plus screen share session. Capture live traffic, freeze a frame, walk through it byte by byte, show how invisible problems suddenly become obvious. The mental model to lock in an Ethernet frame is not a container, it's a contract. Synchronization, identity, structure, integrity. Once you see frames that way, Ethernet stops being mysterious and starts feeling predictable even when it fails. And that predictability is exactly what industrial engineers need when Ethernet becomes the backbone of control.